Hi. Some of you had to go to learn about CPR today and miss class, and so I wanted to give you a quick overview of some of our basic derivative shortcuts. And the first one is the derivative of a constant. So, for example, if the function is really just some constant, and I want to find the derivative with respect to x of that function, it's really talking about finding the derivative with respect to x of that constant. Well, the derivative of a constant, let's think about this graphically. Here's the graph of a constant, y equals c. What kind of slope do we have here? The derivative or slope of a constant is always 0. So our first derivative shortcut, the derivative of a constant is 0. If y equals 4, then y prime equals 0. If y equals negative 2, then y prime equals 0. The derivative of a constant is 0. Please pay attention to the notation that I'm using here. I'm using the imperative form of the verb to take the derivative of both sides of this equation. Take e the derivative of f with respect to x. Take e the derivative of c with respect to x. And this problem is made easier because there ain't no x's over here to worry about. It's just the derivative of a constant. And we know that derivative is 0 because the slope of any horizontal line is 0. Okay, 2. We already explored this with the microscope rule. Number 2, the power rule. This is common. It's the one that many of you know about. So if I have y equals x squared, then y prime is 2x. And if I have y equals 3x squared, then y prime equals 6x. And if I have y equals x to the third, then y prime equals 3x squared. And if I have y equals negative 4x to the third, then y prime equals negative 12x squared. So, can we come up with a rule? Well, we know if y equals x to the n power, then y prime will be n to the x, n times x to the n minus 1 power. And we see that here. Here's my n of 2. I bring my 2 down in front. 2 minus 1 is 1. And here I see it again. I bring that 3 down in front. 3, and then 3 minus 1 is 2. So whenever I have x raised to the n power, the derivative will be n times x to the minus n. We can say if we have y equals c times x to the n, some constant, then y prime is going to be nc x to the n minus 1. And that's what we see here. Look, there's a 3 down in front already. We bring down the 2. 2 times 3 gives us 6. We subtract 1. We have 1. Here we have a negative 4 in front. That's our constant. Our power is 3. We bring down the 3. 3 times negative 4 is negative 12. Don't forget to subtract 1 up here. So here's the derivative using the power rule. Power rule. Okay, next. And we've sort of hinted at this one just now. When you have the derivative of a constant multiple. What's that mean, Mr. Kukla? It means that y equals c times f of x. The derivative is just going to be c times f prime of x. Whatever this constant is, I can just take the derivative of the function and multiply that constant to that derivative. So we just saw that if y equals x squared, then y prime was going to be 2x. And now we've got, aha, what if there's a constant in front? So if y equals 3x squared, then y prime will be 3 times the derivative of that function, which is 2x, or 6x. Now, I know we just looked at this and said c times n x to the n minus 1. But this shortcut rule with a constant, this only works for power functions. And we're going to be taking derivatives of all kinds of things that have a constant in front, like what happens if y equals 2 cosine of x. Well, I know that's going to be the derivative of cosine, which I'm not going to tell you right now, times 2. Okay, so we're going to be just taking the derivative of the function and then slapping that or multiplying by whatever constant we have. Okay, next, 4. 4 is the derivative of a sum or difference. So if I have y equals f of x plus or minus g of x, this derivative shortcut says that y prime is simply going to be f prime plus or minus g prime. So if I'm looking at something like y equals x to the third plus x squared minus x, well, y prime will be the derivative of this, 3x squared, plus the derivative of this, which is 2x, minus the derivative of this, which is 1. Okay, so we've got the derivative of a sum or a difference. And here I'm using power rules, but like I said, later on we'll have things like tangent x minus secant x. And we know that the derivative of tangent x minus secant x will be the derivative of tangent x minus the derivative of secant x. More about these later. Right now, we're just saying, look, if you've got this polynomial and you want to take the derivative of each piece and you're going to be good to go. That's number 4, the derivative of a sum or a difference. Okay, 5. 5 is the product rule. And what's really important to know about the product rule is the derivative of a product is color change, not the product of the derivatives. What does this mean? Well, it means that if y equals f of x times g of x, then y prime is not going to be f prime of x times g prime of x. I know that worked with sum and difference, but it does not work here. You cannot do this thing. Instead, we have to use this thing called the product rule, which you're going to need to memorize. Because you already had to suffer today, will not show you the proof of the product rule. But if you want to see it, come by and I'll show you. Okay, so let's go back to y equals f of x times g of x. If we were to derive the product rule, dy dx, or y prime, would be, here it comes, this times the derivative of that, g prime of x, oh no wait, plus this times the derivative of that, f prime of x. So what does that look like when I use it? Well, let's see. If I have y equals x squared plus 2x times 3x minus 5, there's my f, there's my g. Y prime is going to be this, x squared plus 2x times the derivative of this. The derivative of 3x is 3. We know the slope of a linear function is that slope number there, and the derivative of a constant is 0, so the derivative of 3x minus 5 is 3. Then, don't forget, plus this 3x minus 5 times the derivative of this. Well, we learned a few minutes ago that the derivative of a sum is the derivative of each of these pieces. The derivative of x squared is 2x, then we have our plus, and the derivative of 2x is 2. Yes, it would be good for you to be FOILing this out, or distributing and combining like terms. Sometimes that's going to be too heinous to do, but when we get to chapter 5, we're going to be setting derivatives equal to 0, and so we're going to want them in factored form. So I'm going to practice a little bit now, when it's not too painful, getting accustomed to having derivatives equal to 0. Okay, so there's y prime. Now, it is true that if you were to FOIL here, x squared plus 2x, 3x minus 5. If you were to FOIL this out, you'd get y equals 3x to the third plus 6x squared minus 5x squared minus 10x, and you'd combine like terms and you'd say 3x to the third plus 1x squared minus 10x, and that just gets you to y, not y prime. Now y prime is the derivative of this, so we bring down the 3, we subtract 1, we bring down the 2, we subtract 1, and the derivative of negative 10x, that's a linear function, there's the slope right there, negative 10. So, did we get the same thing? We had 9x squared plus 2x minus 10, and lo and behold, 9x squared plus 2x minus 10. And some of you may be saying, well, Kukla, screw that power rule. There's a product rule. There's no way I'm doing this times the derivative of that plus that times the derivative of that. Well, I just want to say, when we come across this function, y equals sine x times ln of x, all y'all who say, I'll just FOIL it out, you're going to be stuck. You have to know the product rule. So I would say you could check your product rule by FOILing and taking the derivative, but in general, you should be practicing the product rule right now and always. Okay, so there's 2 more rules. Number 5 was the product rule. And again, the product rule is, it's really worth saying again, if I have 3x squared minus 2 and 5x squared plus 7x plus 1, then y prime is this, 3x squared minus 2, times the derivative of this. The derivative of 5x squared will be 10x, plus the derivative of 7x is 7, and the derivative of this constant is 0. But that's only half of the product rule. Remember, plus this 5x squared plus 7x plus 1 times the derivative of this. Well, the derivative of 3x squared, I'll bring down the 2, I'll have 6x. Subtract 1, so we're to the first. And the derivative of this constant is 0. So there we are. I can FOIL this out and combine like terms, but really I just wanted to highlight the product rule. This times the derivative of that, plus that times the derivative of this. And no, the world won't fall down if you say that times the derivative of this, plus this times the derivative of that. That just switches this and this term, okay? All right, so since there's a product rule, there's also a quotient rule. Quotient rule. And our quotient rule is used when y equals f of x over g of x. And guess what? That's not going to be y prime equals f prime over g prime. No, no, no. Don't even think. Again, there is a nice, lengthy, kind of cool, exciting to see proof for this. And if you're thinking about doing a bunch more math classes instead of maybe just one more math class after ours, then I'd recommend you come in and ask me about it, and I'll go through it with you. But if you're just going to take your year's worth of college calc and move on to your architecture degree, then you don't need the proof for the quotient rule. Maybe you're idly curious. You should come in anyway. Say, show me the quotient rule. Okay, so the quotient rule works like this. This is my low function, and this is my high function. And my little song is y prime is low, d high, minus high, d low, over low squared. What you on about, Kukla? Well, I'll show you. So if we have y equals f of x over g of x, then y prime is going to be the low function, g, times the derivative of the high function, which would be f prime, minus, this isn't the product rule. The product rule has a plus. The quotient rule has a minus. The high function, which is f, times the derivative of d low, the derivative of the low function, times g prime. All over, there's a fraction, the low function, g squared. Okay, so that seems pretty heinous. How does it work? Well, I'm going to leave that there, and I'm going to put this on top, and we're going to take a look at y equals 2x minus 3 over 3x plus 4. And I want y prime. So remember, it was low d high minus high d low over low squared. I'm sure there's a nice song you can do. My high school calculus teacher, Ms. Nicholson, taught us the Seven Dwarfs Hi Ho song as the music to low D high minus high D low. But I've never been able to get that work, and I should really call Barbara Nicholson back up and say, how'd you do that? Anyway, we want low, 3x plus 4, D high, the derivative of this stuff. Well, the derivative of 2x is 2, and the derivative of minus 3 is 0. Then remember, low D high minus high, 2x minus 3, d low, we need the derivative of this function. Well, the derivative of 3x is 3, the derivative of 4 is 0. So we're just going to be multiplying by the derivative of the bottom function, which is 3, all over, and this is something that many students forget, 3x plus 4 quantity squared. So we're going to be distributing and combining like terms here. I'm going to have 6x plus 8 minus 6x minus a minus is plus 9 all over 3x plus 4 squared. Or when we combine like terms, we get 17 over 3x plus 4 squared. It's really hard to see how this turns into this without doing low d high minus high d low over low squared. Okay? So we need that quotient rule. Perhaps we should try one together. How about y equals x squared plus 5x minus 2 over 3x plus 1 on the bottom. what would y prime be? Well, yeah, I'm waiting for you to do it. All right, low, d high. What's the derivative of this stuff? Well, the derivative of x squared is 2x. The derivative of 5x is 5, and the derivative of minus 2 is 0. So we just did low d high minus, now we need high, x squared plus 5x minus 2. D low, we need the derivative of this bottom function. The derivative of 3x is 3, and the derivative of a constant is 0. So we just have 3. All over, don't forget, low squared. So if I FOIL here, I get 6x squared plus 17x plus 5 minus 3x squared. And please don't forget to distribute this negative to everything. 3x squared minus 15x plus 6 all over 3x plus 1 squared. Actually, when we get to chapter 5, we're going to want this like this. We're going to want things in factored form. Here, I have to FOIL and distribute and combine like terms because I'm not in factored form. Okay, so I'm going to have 3x squared plus 2x plus 11 over 3x plus 1 quantity squared. And those of you who are already thinking about chapter 5, behold the factors of 33 that add up to 2. There are none, and I'd have to use quadratic formula on that. Oh boy, it all comes to use this year. Okay, so there's the quotient rule, number 6. And number 7 is actually just a variation on one of our shortcuts that we had, the power rule, except now we're going to say x to the n, but n isn't an integer value. N is any rational number. So if I have y equals x to the 2/3 power, well, y prime is just going to be, bring that power down in front, x, and subtract 1. 2/3 minus 1 is 2/3 minus 3/3, or negative 1/3. This is going to be fine for us, but sometimes we see it written as this, and sometimes we see it written as this. And because multiple choice will happily do either of these, you should be comfortable with this. Now, for us, when we're in chapter 5, we're going to much prefer this representation of the derivative. How about this one? If y equals x to the negative 5/3. Okay, I bring down the negative 5/3 when I take the derivative, and I subtract 1. Negative 5/3 minus 1, which is negative 5/3 minus 3/3, or negative 8/3. Oops, not 8/8, but 8/3. Okie doke. So those are the shortcuts that you might have missed in class today. You will need them in tonight's homework. Have fun with that.